the distance between nanoparticle.
Okay, so due to the time limitation, we have to move on to the next speaker.
Okay, our next speaker is Professor Yang from UCLA. Professor Yang, are you there?
Yes, I am here.
Thank you for coming today. So
Yes,
could you please share your slide?
Yes, I do that.
In the meantime, let me briefly introduce Professor Yang. Professor Yang received his BS in physics from National Chung Kung University in Taiwan, an MS and PhD degree in physics and applied physics from University of Massachusetts, Lowell. Before he joined UCLA in 1997, he served as a research staff of UNIX in Santa Barbara. He is now the Carol and Lauren E. Tenas Jr. Endowed Chair Professor of Material Science and Engineering at UCLA. He has more than 400 lab-read papers, including Science and Nature, with accumulated citation more than 100,000. And his H index is over 160. He is a fellow of AAS, MRS, RSC, APS, SPIE. Since 1997, he has supervised more than 40 students and postdocs that have become tenured track or tenured faculty. So he's gonna talk about 2 decades in the making, Yang Lab from organic electronics to perovskite. Professor Yang, please go ahead.
Thank you so much for the invitation. And then let me see, can I do this? Okay. So I'm going to share with you my experience at UCLA, and then I'm going to start a little bit a story about myself. So I came to America to study my PhD in UMass Law, we're in the Boston area, and then in 19. Oops. This is not working. Okay. No, okay, now it works. In 1985 to 1991, and then later I moved to California, to UC Riverside as a postdoc, and then joined UNIX Corporation, and then 4 years later I became an assistant professor at UCLA. So the reason I spent a little bit time explain to you my experience is because that's useful to explain my research later. So my PhD covers from physics for nonlinear optics, and then to electrical engineer. Actually, I work on polysilicon photovoltaic at the time, and then moved to chemistry, working on conjugate polymer. So in 6 years, I finished my PhD in 3 different departments. And it was a very painful experience at the time, but nowadays we call multidisciplinary education. So it's ironically, that was very useful, but a painful experience for me to go through 6 years in 3 different research groups. Anyway, after that, I moved from Boston to California, a place called Riverside, that the place cannot find a river. And then I worked in Santa Barbara. After that, I joined UCLA as assistant professor. I was a 100,000 star package with a 350 square foot. So it was me when I was young, and we demonstrated the first printed organic LED after I joined UCLA. And then our group worked on many different ideas, from OLED, organic LED, organic memory, organic transistor. I want to talk about organic PV today, and also a little bit about inorganic PV, and then metal oxide transistors. So this is my group photo in 2018. At the time, my group has 30 plus people. And so let me start. So this is a little bit introduction about photovoltaic. And so this is solar spectra. And this gray color is where the gallium arsenide is. That so with the right band gap. And then I want your attention to here about 620 nanometer. That would be useful. So the solar photovoltaic is the turning the solar energy into electricity. So the very simple idea from Professor Ilya Yabanovitch's simple cartoon is showing that ideal solar cells is a material with very strong fluorescence. So if when photons comes in, generate electrons and hole pairs. And then if one have, so that's pop out this so-called quasi-Fermi level, which supported so-called open circuit voltage. So the electrons and holes are extracted from the contact, select contact. And then from that select contact forms a photocurrent. Okay, so once you have a voltage and current, it's become a photovoltaic. So the IV curve, typical IV curve looks like this. There's an open circuit voltage, short circuit current, and there's a maximum power point. So the power conversion efficiency is given by this equation is JSC times VOC times the field factor, which is defined in this equation. Basically, field factor is how large this square is. So you want to make a power point, you want to make the maximum power field factor as big as possible. So how to make good photovoltaic cell? You want to make a JSC as big as possible, VOC as high as possible, and field factor as high as possible. So this one relate to absorption. So you want to broaden the absorption of the sunlight, and then you want to have a better material, high PO and long carrier lifetime, and then less defects. So those are the important part. And then you will find this material is actually very important material now called perovskite solar cell, satisfy those conditions. Open circuit voltage, that you want to have a hetero or the homo junctions, and a good contact, as I mentioned to you, is called selective contact. Anyway, so the field factor is to do with the series and the contact resistance. So we start work on organic photovoltaic, and then the mechanism is in this cartoon that's showing that when we blend two different materials, one is donor, the other one is acceptor. So one is pink color, the other one is blue color. And the Venn diagram is like this. When photon comes in, it generates electrons being channeled away, and then the holes are channeled away from another material. So one material is called N-type, the other one is called P-type. So this is constructive as a donor and acceptor concept. So in 2005, Dr. Gang Li, now is a professor in Hong Kong Polytech, joined our group. He worked on the bioheterojunction materials. And so in his research, he found that usually when the graduate student working on this project, what they do is they do the spin coating, very high speed, form a uniform film. But Gang is a very patient person. He found that actually by so-called slow growth, with the exactly same material, you can see when Dr. Gang Li slowly extend the drying time, you can see this curve is getting more, the absorption getting better and better. And then you can see this pi electron interaction start to show up when we dry the film. Instead of a few seconds, you dry the film in a few minutes. Okay, so the longest time you dry, I think, is 30 minutes. So with that, you can see that the absorption is increased. As I mentioned to you, when the absorption increase, the photocurrent increase. So that's a very good observation, and that's established. We push the device efficiency from 1% to about 5% in the natural material paper. The paper has been cited about more than 6,000 times now, very highly cited paper. But I want your attention to this. This is absorption age. So by looking at this absorption age, one can immediately see what is missing is this is solar spectrum, but this part, 60% of energy are infrared light, are not being used. P3HT only utilize the visible part. So the strategical thinking in 2007 was, so this is, the green color is P3HT, is that we want to utilize the infrared portion of the sunlight. So that's what I told my chemist, let's do it. So occupy the infrared highland. And then, so this is 900 nanometer. So so right now we are approaching to 1,000 nanometer absorption. So this is really tremendous. So I put down a timeline of our infrared polymer as a historical event in the past 15 years or 16 years. So our first polymer is this silicon substitute of a carbon called PSBT polymer. And then in 2012, I need to watch my time, we have this 900 to 1,000 IR polymer. And then in 2013, we break the symmetry of the benzene, and then we put the oxygen here, and then we break the first time 10% efficiency barrier of OPV device using the tandem device structure. And then in 2015, we have this ternary OPV, means instead of donor and acceptor 2 compounds, we have 3 compounds into the device. And then we start to work on the infrared acceptor. Remember, we have a donor acceptor system. So our system was a donor and the acceptor, the blue and the red colors. So this is a donor and this is acceptor. So once we done the donor, we start to work on the acceptor. We work on Y1 to Y3. Acceptors, we publish papers in Nature Communication and the Advanced Materials. So that, so now I want to go a little bit into details about our research. So the idea of designing the infrared polymer is this donor acceptor push and pull, electron pushing and pull, withdrawing idea. That is, you take these 2 molecules, you fuse them together by chemistry, synthetic chemistry into it. So there's a band gap becomes smaller. They adopt the Lumon level and HOMO level of the different materials. So this is the material that we collaborate with Sumitomo Chemical. We break the symmetries. Again, I told you with earlier, with oxygen in here. And this material turned out to be very successful. 1.38 EV is perfect band gap. So, and so we have a series of polymer infrared donors by Dr. Hou Jianhui, and then Dr. Dou Letian. Now, Professor Dou is now in Purdue University, and Dr. Professor Hou is in Chinese Academy of Science. So those are the series of polymers that we synthesize. And you can see you push the absorption edge all the way from 700, 800, 900 to close to 1,000 nanometers. So, so a little bit more detail about our research. That is, you can see we start from very low efficiency of 3%, and then we go to a 5% efficiency. And then from when we make material more and more into infrared, and then our efficiency also improve from the 5 to 6%, and then from there, and then we go into the efficiency to 7% now. So those are a series of development in our group, and then the really important part is Dr. Jing Biyu now is a professor now in the Chinese Academy of Science in Semiconductor Institute. So, oops, sorry. So he actually making a tandem device. Remember I told you we have a absorption in the visible. Now we take a absorption in the infrared. Now we turn that into a tandem device, and then this use P3HT. So this tandem device, we break the 10% barrier for the first time. in the polymer OPV record history. So this is very exciting progress. So now we enter the so-called non-fluorine organic photovoltaic. So so this is the non-fluorine materials, and this is material using a 1986 paper by Professor Qing Tan. He was a scientist in Kodak at the time. And then Professor Zhang at Zhang Xiaowei at the Peking University. He was the first one make this ITIC, a non-fluorine acceptor. And then we work on Y1 molecule in my group, and then we publish a paper in the in the Nature Communication and Y1 molecule. And then subsequently we make a Y2, Y3, and our collaborator in China, Huazhong University of Science and Technology, they actually report the Y6 molecule, which has become a more or less like a standard molecule in the organic photovoltaic field. So this is Dr. Do that we make this low bandgap polymer in 2013. This is a donor, and Dr. Dong, Meng Dong, and Dr. Pei, and Dr. Yuan was the visiting student to our group. Jointly, we make this Y1 molecule. It's certified as a world record efficiency at the time. And then, so we're very proud to present to you. This is NREL chart of a world record efficiency, and UCLA has been very proud of. In 2019, we have 2 world records on the NREL chart. That's basically one is the single junction, the other one is the tandem device. So by saying that, that has been a history of the making. So, oops, that's, I think this one, again, okay. Somehow I'm not very familiar with this, but okay, anyway. And so this paper in Nature Communication in 2019. So this one is 12.6% a Newport certified. So this is our Y1 or Y2 molecule as a acceptor, and this is a PBDBT as a donor materials. So we found that is the absorption age, a single junction device, all the way to 900 nanometer, and then cross the spectrometer. So you can see the EQE is 70%. It's not bad, but inorganic semiconductor can go to a much higher value. So that's how they make not band-like structure, not exciton-like materials. So the efficiency is now 12-13%. And but I want you to remember one thing. This is year 2019. So after this paper has been published, the efficiency went up like crazy. So let me show you this one. So, okay, one thing I'd like to share with you is this energy offset, the delta E. The energy loss has been very small. So we are able to use the new material to cut down the energy, the VOC loss. And that has not been demonstrated in organic solar cell. Organic solar cell usually like 0.8 EV or 1 EV, 1 volt. So that's sometimes very high. The exciton binding energy was very strong. Anyway, so the impact of our acceptor Y1 is that the PCE performance from 13% Y1 to Y6 in 15%. So from Y1, 13% in 2019, and then all the way to Y6 in 15% in the same year. So I just want to tell you that those are the work in my group. We look into it. That is, we create a pioneer work. So people who stand on our shoulder can achieve much better value because our earlier work. And so I heard the number now is 19% now, the efficiency. So that is really amazing progress that I'd like to share with you. And so this is the efficiency chart that in my group, we start from 2003. And then through the years, we publish about more than 150 papers in OPV alone. And then these 150 papers, more than 50,000 citations. So each paper is about, average is about 350 citations in the OPV field. Now it's 2020. So our group efficiency is about 17%, 18% now in our group. But more importantly, by working together with with Paul Weiss, we report this so-called transparent OPV. You can see this is a real solar cell. You can see how transparent this solar cell is. And that could be really application for solar windows and other things. So really excited about that. There's one paper I particularly like to mention to you. In 2006, we worked with NREL. We standardized the OPV solar cell efficiency measurement. So that has to be very productive time. Okay. And in addition to that, OPV, our group started to work on 2012, work on so-called perovskite solar cells. So I have only one slide, this slide, because SKKU with Professor Nanyu Park there, and now Professor Jingwood Lee and other faculties there. This is the place that some of the best perovskite research done. So I summarize my research and my group research in this slide. So this is 2012, we started the perovskite research. And then in 2013, we have published a paper on the planar heterojunction device. And then in 2014, we published a paper in Science. Now it's cited by 5,000 times now. Interface engineering, this is very important work. The interface engineering really make the solar cell improve. In 2016, we published a paper in Nature Nanotech on the improve the air stability of solar cell by solution process of metal oxide transport layers. And in 2018, we published a paper using a perovskite and the copper CIGS tandem device. And that is a world record efficiency in the tandem device with perovskite. And then in 2019, we published another paper in Science of the constructed molecule configuration for surface defect passivation and for the perovskite solar cells. And then this year, we published another paper in Science of the reconfigurable band edge state, because we proved the organic molecule was able to modulate the ABX site. We're able to modulate the site of the perovskite band structure. And previously, people think ABX, the A site is organic molecule, has only the mechanical structure. But in this paper, I think it's important for the future perovskite design rules. One can design a conjugate molecule which was able to influence the band edge structure and get a better stability of the device. So my time is almost up, and I'd like to give some time for students to ask questions. So I want to share with you, this is the work by Professor Zhou, Huanping Zhou at the PKU, and Dr. Chen Qi at the Professor Chen Qi at the Beiligung. I don't know how to translate it in English. I think Beijing Institute of Science and Technology And Dr. Jingjing Xue just moved to China, Zhejiang University, and Dr. Wang Rui joined Westlake University as both assistant professor. So I want to give you my acknowledgement. Over the years, our research has been supported by National Science Foundation, Air Force, Office of Naval Research, and DOE. I'd like to thank their financial support. This is my group in 2018. We have a group more than 30 people, actually it's 38, I counted. So, and then I moved, I took 2 years off. I joined Westlake University as a founding dean of school engineering. In China, I worked there for about 1.5 years. and I returned to UCLA. And then I returned to UCLA. I was thinking, what should I do? I don't want to repeat myself. So I decided to reinvent the YY lab. So this is YY lab now. We have only 6 people, myself included. So it's very exciting. And I hope you guys can invite me a year from now that I can share with you what great work we have been doing. So thank you so much for your time. And then I will end my talk here. Thank you.
Okay, thank you very much for a very nice talk, Professor Yang. Now it's time for the question. Is there any question from audience? Okay, actually, oh yeah.
I have
Seems
one
like there's
question for
question.
the OPV device.
Yes, please.
As I know, the organic based solar cell is generally less stable than inorganic based solar cells. So how do we solve this problem?
Well, I wish I can tell you. If I know it, I will become. I start my own company now. There are many. It's not easy. It's not easy, but we are working on it. The fundamental part is understand what caused the degradation and then solve that. It's similar to perovskite. You know, perovskite also not very stable. So many people, ourselves included, understand the ionic migration and other things. In OPV, similar questions arise. Okay.
Then seems like Zhong Wenting, please turn on your voice.
Yeah. Hello, Professor.
Hi.
I want. Wait, can you hear me?
Yes, I can. I can hear you.
Yeah. I want to ask. I saw your PowerPoint. When you design the acceptor from Y1 to Y6, these are polymer and their molecular structure is complex. But how to design this kind of material and improve it from Y1 and Y6?
Oh, rule number 1: get the best people to work together. So we have some of the best chemists in our lab, and also we collaborate with many people. So that's why they come and educate me. But more importantly, I was not trained as a chemist, I must say that. So a lot of times we work together or come out new ideas together. So I often share with them what we need and they went back. So Y1, for example, Y1 was a joint thinking between the visiting student, my postdoc, Pei and Dong, and they have come out this idea. So together, so they should take major credit.
Okay, thank you.
Sure.
Actually, I also have a quick question.
Yes, go ahead.
Professor Yang, you have been trained more than 40 students and postdocs that became a faculty, right?
Yeah.
I think there are many students who want to be a faculty in the future in this conference. So do you have any advice and qualification that you think the most important qualification for the faculty?
Rule number one, don't trust your advisor too much. Challenge your advisor. That's rule number one. And number two, don't trust the textbook too much. So my idea is that I actually talked to a professor today, the other one. Being a good professor, faculty, I'm talking about the research part. We constantly has to ask a simple question, that is, are we working on the most important and fundamental questions? So back to the question the lady asked me earlier, the Y1 to Y6 molecule. Once we have the Y1 molecule, design. And then there becomes the side group substitute, you change this side group, that one. So important part is what is the main frame of this organic molecule being conceived? That's what the lady, she asked me. So on the other hand, constantly ask questions. So that's why when I came back from China, from Westlake University, I sit there, I look at my group, and that's why I also question myself. I say, what do I want to do? For example, I'm more than 60 years old. I say I have another 10 years of research, active research time. What do I want to do? What do I want to make an impact? So that's why I also want to reinvent myself. That's why I put the sentence there, share with you. So if I have a chance to come back a year next year, I will be more than happy to share with you what we have done.
Yeah, thank you for a very nice talk. And I think it will be very helpful for the students.
Thank you.
Thank you, Professor Yang.
Yeah.
Let's move on to our next speaker, Mr. Gonu Park from SKKU. He's gonna talk about azeotropic effect of humidity on methylammonium chloride for highly efficient formamidine-lead triiodide perovskite solar cells. Mr. Park, please go ahead.
Sorry. Thank you, Professor Lee. So good afternoon, everyone. I'm Kwon Park from a graduate student from Sungkyunkwan University at the Advancing Institute of Nanotechnology. My advisor is Professor Sinuk Lee. Today I will be presenting how humidity affects on the methylammonium chloride additive for fabricating highly efficient formamidine lead iodide perovskite solar cells. Okay, so recently perovskite solar cell has been drawing great attention due to its efficiency, deliver 25.5% from 9.8% within a decade, which is now very comparable to well-established silicon solar cells. Sorry about that. So silicon solar cells. The perovskite is a crystal structure with the general formula of ABX3, where A is a cation, B is a metals, and X is a halide. As you can see here, within this structure, the structure is interconnected to octahedra. In the center of the octahedron, you have a metal, and in the corners you have a halide, and then in the center of the lattice, you put the organic cation. Within this structure, you can select the various components to create the various type of the perovskite materials, as long as the tolerance factor for the formability is allowed. More than that, the perovskite exhibits very high crystalline with different less properties, and it exhibits a high absorption coefficient. And more than that, the perovskite the fabrication process of the perovskite solar cell devices is very easy, and the cost is very inexpensive. So therefore, these properties are making the perovskite as the promising candidate for the next generation solar cells. Okay, so recently, among the perovskite materials, the formamidine lead iodide or FAPBS3 perovskite has been widely studied because of its excisional band gap close to the ideal value of the single junction cells. The FAPBS3 has two major phases, hexagonal and cubic phase, or also called as a delta phase and the alpha phase. By the annealing at the high temperature, the delta phase converts to the alpha phase, becoming photoactive states. However, once the alpha phase forms, it readily converts back to delta phase because of the large Fa cation inducing the lattice strain, which destabilizes the lattice stability. And then by the exposure of the humidity, it gradually increases the surface defects, which accelerates this process. So in order to improve the phase stability, the additive engineering is highly required. And that's recommended. So methylamine chloride has been frequently reported as to be an excellent stabilizer of the alpha phase FAPBI3, and then most of the breaking records of the power conversion efficiency of the FAPBI3 solar cells are containing MACL additive as an excess. The beneficial aspect of the MACL additive is it can act as a stabilizer, where the MACL can initially incorporate it into the FAPBI3 lattice, reducing the lattice strain during the annealing process, and then MACL can be sublimated or evaporated during the annealing process, and then they live as a gas phase, which prevents the unwanted bandgap widening or compositional changes of the FAPBI3. And also, it can enlarge the grain size, which reduces the trap density. Actually, the trap density is highly correlated with the density of the grain boundaries. So the MACL is a great candidate for the additive engineering. We've tried to fabricate the devices followed by the previously reported MACL studies. This is the box plot of the efficiency of the FAPBI3 solar cell according to the MACL concentration. They were able to achieve the highest efficiency with the use of the 40% MACL. However, our results came out different, that our optimum MACL amount is somewhere fixed to the 20% MACL, and the efficiency sharply decreases when the MACL content is increased. And we also found that by use of the 40%, the stability becomes very unstable, and the phase instability becomes severe, that the alpha phase readily converts back to the delta phase within a day. So, and we also noticed that the suggested amount of the MACL are varied by the many publications, and then the fabrication environment is often insufficiently provided from the many papers. So we suggest the conjecture that the humidity might be a main cause for the low reproducibility of the MACL additives. So because the many labs occupy the different facilities and with the different humidity levels, so we thought that the MACL might be a critical factor for determining the MACL content. So in order to investigate the humidity effect on the MACL additives during the annealing process, we designed the fabrication process like this. Fabrication process is divided into two large process steps, pre-annealing step and the post-annealing step. We varied the humidity levels for the post-annealing step. And as you can see here, the dry air and the ambient air, which is said to be a 30% humidity. First of all, we observed that there is a significant improvement of the phase stability from the films annealed under the humidity. The left-hand side is the UV spectrometer, and the right side is XRD. You can see that there is a significant amount of the alpha phase is sustained from the films from the annealed under the humidity with maintaining light absorption ability, while the dry air shows a complete loss of the light absorption with the significant amount of the delta phase is observed. And then we further carried out the in situ UV spectrometer according to the annealing time. The top one is the dry and the bottom one is the humidity. We also observed that there is a significant, notable redshifting onset value changes from the films annealed under the humidity, while the dry condition shows no visible changes, which implies that there is the compositional changes from the humidity condition. So in order to investigate the compositional changes from the humidity condition, we continue to measure the XRD. The red line is the pristine FAPBI3 for the reference, and the wine color line is the pre-annealing condition with the 40% MACL. Top one is the dry, and the bottom is the humidity level, humidity condition. And then these are the zoom-in XRD of the alpha phase of the FAPBI3. As you can see, the compared to the precedent FFPS3, the peak position of the pre-annealing condition shows that the peak is shifted to a higher angle. This is because of the MACL is incorporated into the FFPS lattice, inducing the volume shrinkage. But by the prolonged annealing time, the peak is shifted to the lower angle, which reflects that the MACL is evaporated or eliminated. And also you can see that the humidity condition shows much lower peak position to that of the dry condition, which implies that the MACL is facilitatively eliminated or evaporated during the annealing process. The finalized films of the both film, the result of the TOF sim showed that the compared to the dry sample, the humidity condition shows a lower content of chloride. And then to determine why the MACL evaporation or elimination is facilitated by the humidity, we continue to check the TGA coupled with the DTA analysis. We prepared the two samples. Interestingly, we observed that the MACL exhibits a very hygroscopic characteristic that it becomes liquefied within a day after exposure to humidity. So we continue to measure the TGA. The top one is the dry MACL sample, and the bottom is the liquefied MACL. Both samples exhibit the endothermic process, which absorbs the heat to decompose it, for the decomposition. But there was a initial weight loss, significant initial weight loss observed from the liquefied MACL at the lower temperature. So what, to see what's happening at this lower temperature, we also carried out the mass spectrometry, and we found that the MA and then the CL fragments were detected at this lower temperature, which means that shows that the MACL is the facilitatively decomposes at the lower temperature. So we conjecture that the MACL, this is the positive azeotropic effect of the water that lowers the boiling point of the MACL decomposition or evaporation. So we continue to check the PL emission. We continue to check the PL emission with the SCSC measurements. We found that there is a significance of the PL emission, which is about 100-fold to that of the dry condition from the humidity condition. That and then we found that the humidity condition exhibits the longer Taylor time with having lower density trap density. And then we were able to achieve the 21.86% of the PCE with a negligible hysteresis, and along with the noticeable improvement of the VOC open circuit voltage and the short circuit current, which resulted from the lower in trap density. So in summary, so the MACL exhibits a very high hygroscopy, and the humidity might be inducing the lower, causing the lowering the boil points of the MACL during the annealing process, and then by the sufficient removal process of the MACL, the trap density is reduced with improvement in the open circuit voltage. Okay, thank you for your attention.
Okay, thank you for a nice talk, Mr. Park. Due to the time limit, we probably have one quick question from the audience. Is there any question?
Hi. Let me ask you a question.
Yes.
Thank you
Yes,
for
please.
your presentation. Polymer research is difficult to synthesize. I know that material with irregular property.
Let me ask you a question. It seems like there is a significant difference in power conversion efficiency when you anneal the film in the dry condition or the condition with humidity? Is it because you add the methylammonium chloride as an additive? So what is the origin of the much inferior efficiency that is the film annealed in the dry condition? Is it the methylammonium or the chloride anion?
I think, thank you for the question. I think the chloride anion is I think the main cause for the destabilizing the phase stability of the FAPUS3. Actually, we experimented that for determining which component of the MECL destabilizes and lowers the phase stability of the FAPUS3.
Okay. Okay. Thank you. This is the. Let me wrap up the first session in the afternoon. We're gonna take around 10-minute break and then continue to the second session.